today. Let's take a look at just a couple simple area formulas. Start with a triangle, and then we'll look at a polygon. And we'll do this pretty quickly so you get a chance to work on this stuff. We know that we can calculate the area of any triangle with a base length b and a height h with our old standard formula, area equals 1/2 base times height. Always works, right? That's fine, but the downside of that formula is it depends on two different things. It depends on knowing the base length and the height, right? In certain circumstances in math, when things are really regular, like with an equilateral triangle, we can turn that formula into something that's a little better, something that only depends on one measurement instead of two. And we can, in this case, we can develop a formula for the area that depends only on the side length. And I think I told you what the formula was yesterday. Maybe. That's it, right? Did I mention that to you? This is the formula we use. The area of an equilateral triangle, where all the sides are the same length, and we'll call that side length S, how about? The area of the triangle is always just going to be the square root of 3 divided by 4, that fraction, times S squared, the side length squared. Okay, it always works. That's pretty nice because I only have to know one measurement and I can come up with the area. So we're going to use that. That's good. So there's one you get that we'll be able to use. If we wanted to, for example, calculate the area of an equilateral triangle with 8-inch sides, then all I would have to do, let's not even mess with this, let's just do this ourselves. All I would have to do is use my formula. Area equals the square root of 3 over 4 S squared, and what am I substituting? Yeah, 8 goes in for S, perfect. So that's going to look like the square root of 3 over 4 times 8 squared. And that's really just 8 squared over 1, isn't it? If I want to multiply fractions. What's 8 squared? 64. 64. Okay, so this looks like the square root of 3 over 4 times 64 over 1. Now when I multiply fractions, I just multiply straight across, right? So on the top, I'm going to get the square root of 3 times 64, but whenever we multiply a number by a radical, we always want to put the radical last. So we end up with, on the top, 64 radical 3. On the bottom, we get a 4 times 1, and 64 over 4 reduces. Right, 4 goes into 64, what, 16 times? So that's just going to become 16 square root of 3. Okay, that reduces to just a single 16. Make sense? Okay, a lot easier. Look at the alternative. Maybe you don't realize how good this is until you see what the alternative is. The alternative, I would have had to have done this. I'm not going to go through the whole process, but I'll let you see how much better this is. If my equilateral triangle had side length 8, and I wanted to use the old standby, 1/2 base times height, look what I would have had to have done. I would have had to have turned this into a right triangle, and this would have been 4, and that would have been 8, and I would have had to have calculated the height with the Pythagorean theorem first, and then I could have done 1/2 the base times the height, but I would have had to go through that whole Pythagorean theorem process. That's not as easy, is it? What we did was better, simpler. Okay, so that's good. That formula works well. All right, moving on. Okay, so if I want to calculate the area of a polygon, and we're gonna deal with regular polygons. We're not going to deal with weird ones. Ours will all be regular. Then to do that, we need to know this other quantity that's called the apothem. The apothem is defined this way. It's always going to be the perpendicular distance from the center of the polygon to one of the sides. In other words, if I were to create a triangle that links the center with 2 consecutive vertices, so there's my triangle I'm going to create. Now, if this is a regular polygon, how many of those triangles would I add together to make the whole shape? Well, as many as there are sides, right? So I got 1, 2, 3, 4, 5, 6 in this case. Does that make sense? I could break this up into, if I wanted to, I could break this up into 6 of those triangles. This is just one of them. So I could get that area and multiply by 6, right? To get that area, I need to do 1/2 the base times the height of the triangle. Well, the height of the triangle is what we call the apothem of the polygon, right? And so what I would really end up doing to calculate the whole surface, or the whole area of this thing, would just be 1/2 times the base, which is just going to be the length of one of the sides of the polygon, right? So we'll call that S, times the height, which is the apothem, 1/2 base times height, times 6, because there's 6 sides, right? Now look what I can do with this. What is, if the side length is S, what does 6S mean? If there's 6 sides on this thing, if I multiply one of these sides by 6, what am I actually calculating for the polygon? What do you think? The perimeter. Yeah, that's just perimeter, isn't it? Right? So if I rearrange this a little bit, and I make this instead 1/2 times 6S times A, that 6S really just means perimeter, right? And so the area really just ends up being 1/2 times the perimeter of the polygon times the apothem. That's my formula, right? That's pretty good. Now I've got this handy-dandy formula for calculating areas of polygons. I don't have to break them into small pieces anymore, okay? And if that apothem thing is a little bit bizarre, let me just show you one more example of that. Let me pull up a polygon out of bounds. Does everybody see that when I say the apothem, what I'm really talking about is just this distance from the center to there? That's A. Does that make sense? Okay. So let's look at one quick example. So we get this formula. There it is. Area of the polygon is 1/2 the apothem times the perimeter. Okay. Let's try that. Here's the situation we got. Look at one example. We want to find the area of a regular dodecagon. So that's a 20-sided shape. Is that right? Yeah, 20-sided. And so let's see. We get this situation where this Foucault pendulum at the Houston Museum of Natural Sciences in Houston is a regular dodecagon with side length of 4.3 feet, and the radius of the circle that contains it is 8.3 feet. So all that means then is, if I go back to my picture, if I were to enclose this in a circle, I won't draw this very well, but you get the idea. If the radius is 8.3 feet, then isn't that also the distance from the center to one of the vertices? Because that's where the polygon's going to touch the circle, right? So that's going to be 8.3, right? Okay, so then we want to come up with the area of that polygon. Okay, so there's the polygon. That's 8.3 feet. That's 4.3 feet, right? If I want to do that, I just need to know what the ingredients are in my formula. Well, we said that the formula for the area was just 1/2 the apothem times the perimeter. Now, I could calculate the perimeter pretty easily, couldn't I? So I've got 12 sides, not 20 sides, sorry. 12 sides. Each side has a length of 4.3 feet. So then isn't the perimeter just 12 times 4.3? So 51.6 feet. That's the perimeter. That's easy. What I need is the apothem. Okay, to get the apothem, that's just this distance right here, isn't it? Okay, well, I've got enough information there to get it pretty easily. Right, if I know that this distance is 8.3, and that whole distance is 4.3, from there over to there, then that's just half of it, isn't it? Right? So let's blow that triangle up and see this thing a little bigger. there's my triangle. 8.3, this is 4.3, so then half of that would just be 2.15. Right, I'm just going to focus on this right triangle. In fact, let me highlight this in red so we can see it better. This is what I'm focusing on, is just that right triangle right there. 2.1 feet is that length. 8.3 is the hypotenuse, and that's the apothem. Okay, so all I've got to do to find A is just a little Pythagorean theorem stuff. Right? I know if it's a right triangle, isn't A squared plus 2.15 squared 8.3 squared? Right? By the Pythagorean theorem, A squared plus B squared equals C squared, where C is the hypotenuse. So if I get A squared plus 2.15 squared equals 8.3 squared, then isn't A squared, if I just subtract that to the other side, isn't A squared just 8.3 squared minus 2.15 squared? And those are just numbers. I mean, they look, it looks complicated because they're being squared, but they're just numbers. I can put them in a calculator. And then to get A by itself, what do? Square root, sure. And so I just end up with that, right? Okay. Now, they do something on here that is really not very good, and I want to just mention this briefly. Don't, when you're doing these calculations, round in the middle of the calculation. You want to just not round until the very end. You want to put that in your calculator just like that. That's fine. It's easier to do on a graphing calculator than it is on a regular calculator or the Windows calculator. I'm going to give you my quick little sales pitch. You're going to need those. You have to have them in Algebra 2. So you're going to need them pretty soon anyway. If you don't have one, talk to your parents about that, because now would be a great time to do it. For the rest of the year, we end up doing a lot of these big, crazy calculations. You don't need one for it, but it makes life easier, and I will show you how to use them as you're doing this stuff, and you'll feel more comfortable with them next year. Don't have to, but recommend it. So then this is what A is. We already knew that the perimeter was 51.6, I think we calculated, right? So then we can just plug all this stuff into our calculator. In our calculator, we can say 1/2 times that square root times 51.6 and hit enter. And that's what we get. Okay? We don't have to turn that into a number first. Just leave it in your calculator as the square root of some stuff in parentheses. And your calculator then will keep all those digits of accuracy. You're going to need some practice on that, but we'll do that in the lab. Okay? Make sense? So that's how we can calculate these areas of polygons. Not that big a deal. Alrighty, let's go practice. I want to see, give you a chance to work on this and ask questions.